All right, so now we're going to look at some motion graphs going backwards. All right, so we're going to start with this. All right, we've got an acceleration graph, and you can see that it's just a flat line. So it's a constant acceleration of about 1.5, and we'll make these, the acceleration will be in meters per second squared. All right. So flat line on a graph on an acceleration graph is telling you constant acceleration. So we just know here that acceleration is 1.5 meters per second squared. There is actually you could take this if you were to have a slanted line on an acceleration graph. There is a further derivative of this, like the rate of change in acceleration for an object is called the jerk of that. There's even a derivative of jerk that's called jounce, and further derivatives of those, which are just called like higher level derivatives. But we'll stick with the ones that we're going to encounter here. We won't encounter jerk. So if we have this constant acceleration at 1.5 meters per second, right? It's positive acceleration. What that tells us about our velocity graph is because the acceleration is positive, the slope of this velocity graph is going to be such that it's going to go up and to the right. All right, no matter what the beginning velocity was. So if it was something that started from rest, right, we would start right here with a speed of 0 or a velocity of 0, and the graph would slope upward at 1.5 meters per second per second. So let's see. So 1.5 meters per second is here. Per second would be right there. Another 1.5 would take us there. Another 1.5 would take us there. There. So we'd end up with a line that looked like that if we were starting from rest. Right now, similar to your running or your moving man simulations, we're going to start this one off with an initial velocity. All right. They've already actually graphed out positions over here. So this is how the position graph is going to look based off of the information we're working with. So you can see that the position is going from +5 in the negative direction to start. So if an object is moving in the negative direction to start, its initial velocity is going to be negative. All right, so I've assigned this one an initial velocity of -6. And so if the acceleration is 1.5, positive 1.5 meters per second, we'll go up here, and here, here, here. And we have a graph that ends up looking like that. Now, physically, what this would look like then is if we had that's the origin point right there, and this is position 5 over here. I put the initial position to be 5. So this graph, or these sets of graphs, represents a person that started here. They went in this direction until they reached a point of -7 meters. So that's 5. That means -7's out here someplace. So they got all the way to here, stopped, and turned around and started going back. Right, much like you had your moving man doing in your simulations. Okay, so if you are in calculus, you are getting to a point where you're starting to do derivatives, and from those, like you could take a sloped line like this, and what we'd have is slope of that line is 1.5, and the y-intercept is down here at -6. So you could take that and do a derivative and come up with that acceleration over there, or we can just know that the slope of a velocity time graph, this, is an object's acceleration. All right, so slope of a velocity graph equals object's acceleration. All right. Mentioned in previous video, but write it out here just to be safe. And so we could, again, take different ways to interpret this. If the slope is up and to the right, so positive slope means it's a positive acceleration. It kind of depends on what direction the object is moving at first as to what that means. So here we had our dude moving in the negative direction to start. So if he was moving towards the negative, so this is x naught right there, initial position. The initial velocity vector would look like this. But the acceleration vector would look like this. And so, because the acceleration vector is in the opposite direction of the initial velocity, that dude's going to be slowing down to start. And it turns out that at position 1, after his beginning, he gets all the way over here. So that'd be position 1. And at that point, right, position 1 is at time 1. So at 1 second, his velocity is slowed down to negative 4.5. So if this is the initial velocity vector, we take 3/4 of that, and be the velocity vector here. The acceleration vector. All right, the question is, what would the acceleration vector look like in this case? So think about it. Pause the video to think about it if you need to. But at this point, the acceleration vector, the way we would draw it, would be exactly the same as what we drew it over here. Because we said right from the start that the acceleration was constant. So here, the acceleration vector would look like that. Still the same length, still pointing to the right. After 2 seconds of travel, this dude has made it to the 4-meter mark, which is somewhere in here. And after 2 seconds, 1 second, there's 2 seconds, the velocity is slowed to 3 meters per second, so half of the original velocity vector. And the acceleration is still this. Still the same acceleration. And we could take this out further, At 3 seconds, the guy is right here. The velocity vector is down to half of even what it was the second before. Acceleration vector would still be the same. At a time of 4 seconds, the person reaches this point right here, the minimum on the position graph, position -7. And right there, at that point, at 4 seconds, right there, look at what the velocity is. The velocity is 0 at 4 seconds. All right, so that's what this graph is showing us here, that this person was moving in the negative direction. Their velocity was getting closer to 0. So the tough part about this velocity graph is that because it's sloping up and to the right, the interpretation that our brains will give us at first is that the velocity is constantly increasing. what it's doing is it's constantly getting more positive. So if it starts off negative, it starts off as a velocity in the negative direction. As it's getting more positive, at first it's getting closer to zero. So if you have a velocity graph like this where the initial velocity is in the negative and it gets closer to zero, this portion of the graph means that the object is slowing down. Right here, where the graph crosses the time axis, that's where the velocity is zero. So this moment in time right there, at the 4-second mark, that object is not moving. And that's reflected here as well. All right, so the object is moving in the negative direction, moving. And what we can see is with each passing second, here's 1 second, the rise over run for this, the average slope for this time interval is greater than the rise over run for this time interval. And it's much greater than the rise over run for that time interval. And the rise over run for that one is less as well. So if you look at this in terms of rise over run, what the average slope would be, the average slope is decreasing for each one of these, right? Now the slope of a curved line, what you would do is you pick out any point and you draw a tangent line for it. So the tangent line gets closer and closer to being vertical as you go up on this. And as you go down on this curve, it gets more and more towards being horizontal. All right, so that horizontal slope at the very bottom of that curve means this is the point where the object stopped and then started going the other direction. This one's, so that's kind of easier to visualize, I think, than this. It's important that we remember, that we note that negative velocity just means it was moving in one direction, and an increasing acceleration, or excuse me, I should say a positive acceleration, that means velocity is getting more positive, means it's getting closer to zero to start. All right, this is zero velocity. This means not moving for that little brief moment in time. And then it gets faster over there. We could also look at this in the opposite way. Let's say the acceleration that we wanted to look at was negative 1.5. So if we started with a positive velocity, if we started up here, we get a graph that looks like that. And so our brain will tell us, all right, moving down and to the right for velocity means it's slowing down. Yeah, because we started with a positive velocity, so we started with an object that was moving that direction, and its velocity was getting closer to zero. Here's where it hit zero, so it stopped. And then its velocity started getting more and more negative on the other side of that line. So it just means it was moving back the other way and getting faster as it did so. So again, that's what's tough about motion graphs, is they're not always the most intuitive things in the world. We'll do some more examples.